Okay. Doesn't look like too many gained too much weight.
Because we didn't have the leftovers.
Then again, it doesn't look like you all are really droopy-eyed, like you've been staying up really late in the lab either. Anybody got Lab 9 done? Anybody got Phase 1 of the Lab 9 done?
How can you tell?
How can you tell if it's done? Did you send me a mail asking how to test it? And I never replied? Yeah, I remember now. I'm pretty good at answering other emails. Figure you can figure that one out yourself.
Our only solution was to do the rest of the lab.
Well, the way you test your PCP semaphores to see if they work, you have a whole bunch of processes, make them share critical sections, and if you can never see that a critical section gets whacked, then you know that your PCP semaphores aren't working. If a critical section gets whacked, so if two processes are in a critical section at the same time, then you got a problem. So in other words, if you have a whole lot of processes and all that they're doing is shared critical sections and they're all sharing the same PCP semaphore, and you have a printf in the middle, and one process's printf overwrites another process's printf, your PCP semaphores aren't working. But in order to make that work right, you've got to make sure that the prints that each of your processes are printing are completely distinct. So you print ABC in one process and DEF and GEH, or make sure they're all printing different stuff. Have all your processes have different code, and make sure that they're all printing in a critical section, and then that's the majority of the time that the process spends. So that's how I test it. So, announcements. Lab will be held on Thursday instead of Tuesday this week. Rohit is unavailable for lab on Tuesday. You can still use the lab room on Tuesday, but he just won't be there. So Thursday he will be there during the corresponding lab slot. Okay? Practice problems. These are problems that I've given out as homework problems in the past, but I'm not going to give them as homework problems for you. See, I'm kind of nice. But I would suggest that you work on these practice problems sometime between now and the final exam. And that way you can get sufficient practice working problems so that you can do final exam problems. Yes, Ben. What day is the final? Friday the 11th. Is it at 9:30? And don't even think about asking to take it early or late. You have to be here. You have to be here at the scheduled time. It will be in class. Okay. Any other questions? Mitch?
With PCP semaphores.
Oh, and by the way, on that comment, if you're a distance student, we got to talk about what we're going to do for logistics on the exam, but it'll be held at the same time. We'll either have a proctored, or if you guys are going to come up here, then we'll deal with that. So, anyway, Mitch.
So you can't really do the trick with making a process block itself with PCP semaphores, right? Because they don't even...
Yeah, so a PCP semaphore you should not use to make a process block itself, because you can't not get a PCP semaphore. What? You can't not get a PCP semaphore.
So if you have two processes that share PCP semaphores, how can the lower priority process ever get it?
If you have two processes that share a PCP semaphore, how can the lower priority process ever get it?
Yeah.
Well, you have to have a slot where the higher priority process doesn't want it.
But
And it doesn't want the PCP semaphore and doesn't want the CPU.
So it has to block on
It has to take itself out of contention for some point.
Okay.
There has to be slack in the schedule to allow lower priority processes to run. Can somebody explain to me why you can't not get a PCP semaphore? Okay, so that explains why you get it and what happens when you get it, but why can't you not get it? So if Okay, so if the PCP semaphore is already owned, can you ask for it? You can't run the instruction that calls PCP-P. You don't have high enough priority to run. If the PCP semaphore is currently owned, well, I suppose there are scenarios in which that wouldn't be the case. If, for example, you grab a PCP semaphore and then you grab a strong semaphore and block, that would be bad. But if you have high enough priority to ask for the PCP semaphore, that means no other process with higher priority than you is contending for that PCP semaphore at that time. So therefore, you get it. And as soon as you get it, your priority is elevated up to the ceiling priority. Can you get preempted while you own the PCP semaphore? Okay, who doesn't want to vote? All right, all y'all got to vote. Too late, Jake. Who votes you can get preempted while owning a PCP semaphore? Who votes you cannot? Looks like Levi wants to lose points. Did you vote? You voted? Okay. All right. Rat. So, what's the right answer? Both. It depends. What if you have a high priority process that contends for no semaphore? Can it preempt a process that owns a PCP semaphore? If that high priority process has priority higher than the ceiling priority of the PCP semaphore. There's nothing saying you can't preempt that process. So, therefore, if you can preempt a process that owns a PCP semaphore, what is the process that you're preempting that owns the PCP semaphore? What's it doing? It's executing its critical section, right? You grab the PCP semaphore and you execute your critical section, then you release your PCP semaphore. Can you interrupt the critical section? Okay, somebody define for me mutual exclusion and critical section. They're effectively the same thing. This is one y'all botched on the midterm. Oh, some of you quoted me directly, even down to my poor grammar, and then some of you quoted the book, and some of you just kind of hashed together your own. I'm not sure how well you understand this or not. Can you interrupt the critical section? So we said that a critical section is a block of code that must appear to execute atomically, otherwise bad things can happen. Right? So what does it mean that a block of code has to appear to execute atomically? The question we have to ask is, appear to whom? Okay, so if we say appear to the user, who's the user? Is the user the guy that's using the board? Is the user a person, an actual real person, instead of a process person we kind of attribute things to? So, how many processes do I have running on my tablet over there? Let's see. We're going to pull this up. Couple more than 10, 15, 20. We've got a lot of processes there running. Okay. Does Windows have a priority scheduler? These processes, do they share critical sections? Windows use priority inversion, priority inheritance? Is Windows a real-time operating system? So, when we're saying that a process must appear to execute atomically, what we're saying is that for any process that cares, the critical section must execute atomically. For any process that doesn't care, the critical section executes atomically anyway. So it's only for those processes which are sharing the critical section which the execution of that critical section must appear to execute atomically. So what they mean by appear to execute atomically is that a process that's attempting to execute the critical section, it can't execute the critical section unless all the instructions of any other process that's inside that critical section complete execution. So for a process that's attempting to execute the critical section, it executes that critical section as if it were a single instruction, uninterruptible with respect to any other process that's trying to execute the critical section. The critical section can be interrupted. It can be interrupted by processes that aren't attempting to access that critical section. Okay? The reason why is because that code's executing effectively, atomically. Any process that's not sharing that critical section doesn't care. Its execution, whether it be interrupting the critical section or not, will not impact the correctness of the program. If it does, then it implicitly shares the critical section, and we should be grabbing the semaphore anyway. Okay? So you can interrupt the critical section. You just can't interrupt the execution of a critical section and allow another process that shares a critical section to enter the critical section. It's a lot of words. Okay. Yeah, Mitch.
With PCP semaphores, you have to assume that there's some initialization stage that occurs before people start using it.
So the PCP semaphore, do you have to assume that there's some initialization phase that occurs?
So you can set series priorities.
Okay, so there would have to be at some point the setting of the ceiling priority. Now, here's the issue. You guys are creating processes dynamically. So your user interface allows the create PCP command, which will allow you to create a new process. You're going to assign, how do you assign a priority for a process? What dictates who gets higher priority and who gets lower priority? The period. So you've got to compare your period against all the other periods that have been, of all the other processes that have been created so far, and figure out where the period of your newly created process fits. So it has to be some priority that's halfway in between the next highest, the process whose priority equates to a period that's next highest and the next lowest. You put it halfway in between those two. So as soon as you can assign a period, if this is a PCP process, now you've gotten a period, you're assigning a priority based on the period. Once you figured out what that priority is, if that process that you're creating shares a PCP semaphore with a set of processes that have already been created, it's possible that the creation of a new process that shares an existing PCP semaphore could alter the ceiling priority of the process. Now, the ceiling priority of the semaphore, the PCP semaphore. So if I've got three processes created, all of them sharing the same PCP semaphore, and I create a fourth process, and it has a shorter period than all those other three processes, well, that means its priority is going to be higher than those other three processes. And if that newly created process shares the same semaphore, because this newly created process's priority is higher, its static priority is higher, if it's sharing the PCP semaphore, that means I have to elevate the ceiling priority of the PCP semaphore. So in other words, I've got to monkey around with the PCP semaphore. Well, how do I monkey around with the internals of the PCP semaphore? The user interface is doing this. The UI process, the lowest priority process, is going to monkey around with the internal values of the PCP semaphore. Is it safe to do that? So that lowest priority process, what happens if some other process owns the PCP semaphore while I'm monkeying around with it? What if the ceiling priority is currently set at 32, and the process 32 owns the PCP semaphore, and I go in and I try to change the ceiling priority to 16? Isn't that going to mess something up? What'll finish before it messes it up?
The process.
The process.
The process that has to be.
So if the PCP semaphore is owned, who can't run?
UI.
The UI can't run. So we're not going to mess anybody up because I'm not going to be running anyway. That is a critical section. So there is this, if you get in the middle of the sequence of instructions where you're modifying the PCP semaphore and you get interrupted and another process runs and it grabs the PCP semaphore and you're in the middle of modifying the PCP semaphore, that's bad. So whenever you modify a PCP semaphore, you need to disable the interrupt and enable the interrupt. Okay? So there are times where the UI process for very short, it better be very short sequences of instructions, gets to run at a higher priority than even the interrupt. And that's just because when you're monkeying around with your process, with your ready queue and your tables, all of those things that are shared between all your processes, you have to make sure that the interrupt, that you don't mess the interrupt up and you don't mess up any other process. So you disable the interrupt very judiciously around those blocks of code that are going to monkey around with other processes. Okay? So you have to, when you create a new PCP process, you have to make sure that you alter the ceiling priority if it needs to be. But before you do that, disable the interrupt, modify the ceiling priority, enable the interrupt. Okay? In your UI process, whenever you add something to the ready table, you need to disable the interrupt, add it to the ready table, and then enable the interrupt. Otherwise, you could leave the ready table in a weird state if you get interrupted in the middle of modifying the ready table. Okay? How do you know if the set of processes that you've created with your create PCP, how do you know if that's schedulable? Can you use your utilization bound analysis? In Lab 8, how did we predict whether or not our set of tasks were going to be schedulable? You calculated the net utilization of all the tasks that were accessing your system, all the real-time tasks. We left the UI process out of this because it's not a real-time task. So we took all of the real-time tasks that had been created, we calculate their CPU utilization, we sum up all of their utilization, and then we compare it against the upper bound as dictated by Lewin-Leyland. And if we are below the upper bound dictated by Lewin-Leyland, then we say, okay, we guarantee schedulability. If we exceed that upper bound, we continue to attempt to schedule, but we report that the bound has been violated. And we say that we can't guarantee schedulability, but we're going to continue to try to schedule. And you can continue to add tasks up until the net utilization gets to some upper limit. Well, that upper limit's pretty close to 90, 95%, something like that. And as soon as you exceed some upper bound, you're going to get a deadline missed. It'll say your deadline has been violated. The task continues to work after it's supposed to be released. So therefore, the system dies. Can you use that same approach with PCP processes? Does the utilization bound tell you anything with a PCP process? Does it give you a guarantee of schedulability? So if you remember, when we talked about the utilization bound, we specified a whole bunch of conditions on when it can apply. We said first, you got a whole bunch of tasks. Second, they're all independent. Third, scheduler overhead is negligible. Fourth, they all have a period, they all have a compute time. If they take the same, we assume that they take the same worst case execution time every time that they run, and we do the analysis at the critical instant where we release them all simultaneously, and we suppose, and we ask the question, can there ever be a situation where this will not be able to be scheduled, such that everybody meets its deadlines? This point of all tasks are independent. As soon as you have PCP processes, they are sharing a critical section. Because they're sharing a critical section, they are not independent anymore. So the utilization bound analysis cannot offer you a guarantee of schedulability. So, does it do you any good? Can you disprove schedulability with the utilization bound analysis? Somebody tell me, what does the utilization bound analysis tell you? What's the ratio of the process's compute time to its period? What are we saying? What do we mean? What does utilization mean? What's that? So it's a percentage of processor time taken by a process. So if we have a process that gets released every so often, and every time it released, it eats this much CPU time, whether that be all contiguously spaced or whether it gets preempted and then eats a little bit more and then preempted and eats a little bit more and preempted and eats a little bit more, whether that all gets contiguously spaced together or it's spread out, we know that when a process gets released, it'll eventually eat X amount of CPU time corresponding to its compute time. So the ratio of the compute time to the period is what tells you what percentage of the CPU time does this process take up. If you want to disprove schedulability, what can you use utilization to tell you? Calculate the utilization, how much CPU time each of your processes in your system. Can you tell me an upper bound? Can you say if my utilization is greater than 50%, does that tell you anything? What if your utilization is greater than 75%? 80%? What if it's greater than 100%? If your utilization of the total set of processes that you're attempting to run utilizes more CPU than you have, you can guarantee it's not going to be schedulable. So the utilization bound isn't completely useless. It cannot prove schedulability. It can disprove schedulability. Okay? So if your utilization is more than 100%, that means you're utilizing more CPU than you have, and you can't ever win. But if you want to prove schedulability, what can you use to prove schedulability? Given a set of tasks with inter-process dependencies, how can I prove that this system is schedulable or not schedulable? Yeah, the response time analysis. And if you haven't clued in yet, you have to implement that in Lab 9. Okay? So you're going to have to implement that recursive ceiling, blah, 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 all that stuff. Okay, so the response time analysis, if you do it correctly, will give you a necessary and sufficient proof of schedulability. It'll tell you, the utilization bound tells you, I can prove that it's schedulable, but if you exceed the 70% bound, it can't disprove schedulability. Only when you exceed the 100% bound do you disprove schedulability. So it's kind of pessimistic. But RMA will tell you, absolutely, this is schedulable or this is not schedulable. There's going to be some fudge factor because of the fact that you have real scheduler overhead, especially if you put a printf in your ScheduleNext process. But you're going to have to implement response time analysis and let it tell you about whether or not your system's schedulable. You're going to have to apply response time analysis to your software UART and tell you whether or not it's theoretically schedulable. Okay? Yeah.
In class when you did response time analysis, you always assume that all the processes are released together, and when we'll be doing your lab 9, they'll be released, after some time. So how does response time analysis change for them?
Okay, so the question is, in class we assumed that all the tasks were released simultaneously, but in the lab we're not necessarily releasing all the tasks simultaneously. Our contention is, because we're trying to find the worst case response time, the analysis has to be mildly pessimistic, in the sense that it is possible that under some point in execution in your system's lifetime, you will release all of your processes simultaneously. And our contention is it will never be worse than that. So we're going to define the critical instant where we say, let's suppose that all processes are released at the same time. If we can prove schedulability for that situation, we guarantee schedulability for all other combinations of releasing. But if they're all released simultaneously and we can prove schedulability, that's sufficient to prove all of the other cases. So it's mildly pessimistic. There may be situations where response time tells you you're off by a fraction, but you never actually observe a schedulability failure. And that's simply because the response time analysis is very mildly pessimistic. The utilization bound analysis is wildly pessimistic. as you should have observed in Lab 8. Okay. Hope this is helping. I'm just shooting from the hip, trying to tell you about Lab, trying to point out questions where you guys have, where I see people meandering off in the desert in the wrong direction. How do you implement the compute time? Okay, you should have this function you call delay that you call. That function should not read a timer. There's a few of you that say, well, yeah, I know that. It should. There are other people who are attempting to read a timer in the delay function or in the process data structure or somewhere else. You should not compute your delay time by reading a timer. The reason why is because when you swap in and swap out in the middle of accessing a timer, you could end up losing a tick or two, or you could end up losing vast amounts of ticks. So you should calibrate a for loop and see how long the for loop takes to run. And then you should just eat busy loop cycles while you're running your process. So you should know how long a delay loop will take just by how many times you count. So if you count from 1 to 1,000,000, how long does that take? Divide that by the number of the amount of seconds or the amount of ticks you need it to actually take, and then you will know you'll be able to implement a delay loop that'll just count. So no timers for calculating compute time. Don't read a timer. Okay? I've seen that in a few of the people's code that I've been looking at trying to help debug software. What else? Okay.
So you use a timer to calculate how long the for loop takes, right?
You use a timer beforehand to calibrate your for loop, yes.
And then after you know that,
Yes. Okay. Other lab-oriented questions. By the way, what I intend to do for the rest of this week, I've got about 6 pages of notes that are talking about EDF and deadline monotonic scheduling, and that's the last of the material I intend to present. I've posted practice exams for the final. I intend to just be available on Wednesday and Friday to answer whatever questions you have. So I will be here. I'll pull up Wimba and record the lecture. You don't have to come to class if you don't want to. But I will be here and available to answer questions that you may have on the lab or on final exam. So I'll work through final exam problems, and I will shoot from the hip and talk to you about lab questions. Okay? Well, let's just pound through these last few sets of notes here on EDF. Okay. So we think about what we've been doing with our scheduling. This whole Chapter 13 business, rate monotonic scheduling, rate monotonic priority assignment, rate monotonic analysis. Rate monotonic scheduling involves a priority scheduler using fixed priority assignment. What we mean by fixed priority assignment is every process has a static priority. Now we start to blur that fixed priority assignment business just a little bit when we start talking about the PCP stuff, because we can change the priority of a process in accordance with what semaphores it owns. Okay, so but still that's categorized under the broad category of fixed priority assignment, because under normal circumstances a process executes with a fixed priority, and we have a priority scheduler that just analyzes the priority of the task, picks the highest priority task that's available in order to run. There are other options. The other options, so if you consider fixed priority assignment, the opposite of that would be dynamic priority assignment. Well, I guess you could talk about no priority assignment, but kind of nonsense. So dynamic priority assignment. So what you do with dynamic priority assignment is you assign priority based on the current situation at runtime. Basically, this amounts to a decision of who of the currently ready processes should be given the CPU. So your priority scheduler is still a priority scheduler, but you just decide at runtime who has highest priority. Okay? There's a couple of different scenarios for this. How does a desktop processor work? A desktop operating system. So if you're scheduling for So all of you, or a lot of you, had this hard time of when I started telling you, when we started going into in Lab 7, where we implemented the priority scheduler, and we discovered that the high priority task always wins. Well, that's just not right. How could the highest priority process always win? And we say, okay, on purpose, we favor or bias ourselves towards the highest priority process. And it didn't make sense at the time. Why would we want to do that? Because if we got 20 processes, 19 of them aren't ever going to run. Until we got to Lab 8 and we saw this notion of how you can take yourself out of contention for the CPU, and then in the slack that you allow others to run, they get to run. Okay? So not all processes want the CPU all the time. So that's a critical aspect of dealing with the priority schedulers when you are particularly biased toward the process. Well, what if you're a desktop processor? A desktop operating system has got a whole bunch of jobs that it's got to run. Let's say you're running MATLAB simulation at the same time you're doing some Excel stuff, at the same time you're running Word. Well, if you've got stuff that's running in the background, stuff that's running in the foreground, which of those tasks are highest priority? Should you give MATLAB the highest priority, or Word, or your shell? Which one should get highest priority? Well, what happens if you run MATLAB as the highest priority, and it's running an overnight simulation? Can you type email while it's doing that? Can you surf the web? Listen to music? It gets the CPU 100% of the time. Your computer locks. And why does it lock? Well, because you told it to. Okay? So if MATLAB shouldn't be the highest priority process, what should be? How about your MP3 player? If you're using Windows Media Player, you're playing an MP3, should that get highest priority? Well, if it does, it's playing music all the time, so therefore you're never going to get anything done. Well, all right. But I've got a whole bunch of these tasks that are running all the time. And they're always doing, it's not like they're stopping and starting and stopping and starting. It's not like there's a lot of slack. I've got these large tasks that all have to be done, and they're all trying to compete for CPU all the time. If I have a pure priority scheduler for any one of them, I'm going to starve all the rest of my processes until that one process gets completed. And that particularly doesn't make sense if I want to remain responsive to my user who wants to type on his email while all these other processes are running in the background. So what is a scheduling approach that would work for a desktop processor, where I don't starve the prompt, or I don't starve Word or the email client, whatever I want the user to be able to type on, but I still get the work done for all these compute-intensive apps that are running in the background? So you do round robin, start and stop. Okay? So if you use a round robin where you allow each task to have its own little chunk of time, and you run this one, then this one, then this one, then this one, then go back to the first one, the second one, the third one, the fourth one, and go back and forth around like that. What's the computer doing here? Doing math. Moving that mouse around. How'd that work? Don't you think you guys have more computer expertise than most of the people in this valley? 100,000 people in Cache Valley. People sitting here in this room. You know, you don't have more expertise than everybody. There's a few people in the valley that are very good engineers that know how everything works, and people they just know everything. So I think it's safe to say you guys know a whole lot more than a whole lot of the people there. I've already said, maybe I've already made this point. You probably know a whole lot more about computers than the President of the United States. I think we all have used a mouse a few times. Somebody explain to me how a mouse works. Works as an interrupt? What do you mean an interrupt? So you're telling me an interrupt makes this little cursor move around the screen? That's a pretty good guess, Mitch. That's what's going on. It triggers an interrupt every so often, and then you get a little screen update where Windows will go and update that little block of the screen area where you're moving the mouse cursor. What happens if instead of that being an interrupt, that were actually a process? What happens if we were using round robin for scheduling all of our tasks, and I had 30 tasks, all of them getting a quantum of time, and I moved my mouse, it would be very jumpy and around moving like this. So don't I want to have some notion of priority? Don't I want to have my mouse don't I want to favor things a little bit towards my mouse? So round robin with priorities? So there are, you can get really sophisticated with the scheduling algorithms that are applied. Modern operating systems, they have these priority bands. So Windows has them, and so does Linux, but you have these different various priority bands, and you can have tasks allocated to these various bands, and some of them get higher priority. So if one of these in the upper band gets to be made ready and wants the CPU, they get favored over somebody in a lower band. But you can have various priorities within a band. And so if 3 or 4 tasks within a band are all ready, then there's going to be priority allocated in between them. There might be some round robining or some changing and dynamic priority assignment within a band. Usually you don't flip from one band to the next band, but you have processes within a band and they operate. You allocate a band based on level of importance. Like if you were running your mouse as a process, that would get allocated to a high band, because what it's going to do is you'd swap that process in to do a very small, short, sweet thing, and you'd get out of the way very quickly. Okay? So if you have tasks and the fact that your task runs very frequently, in computer terms, your mouse doesn't run really frequently. But the fact is, if you can get that job done very quickly, it gives the appearance of responsiveness. So if you move your mouse and it takes a long time for jittering, it degrades the user's experience very much. So you want to make sure that the mouse appears responsive. So you're going to give mouse processing a higher priority, relatively speaking, than your 10-year MATLAB simulation is going to run. One technique that desktop processors usually use is the following. Okay, so you let a process run for a while, then you let somebody else have a turn. Okay, one way you can implement this, you can assign a priority at creation time to all your processes. How exactly you assign this isn't relative to the discussion at this point, but you can execute priority-based scheduling. Then for each tick or time quantum allowed to the running process, you decrement the process's priority. So decrement in the sense of make it go from a higher priority to a lower priority. Okay? So eventually you'll reset the priority. But as you run this process, you're going to let it run, then you decrement its priority, then let it run, decrement its priority, and you keep on decrementing its priority. Eventually you get to the point to where that process, its priority is no longer the highest priority within its band, and then some other process will be allowed to run. And that way you're still running a priority scheduler, but you're allowing these processes to switch because of the fact that you're decrementing the priority of the process. At some point you'll reset the priority back to where it was before. Okay? So this eventually allows all processes to run. And this is called aging, and it's not necessarily always implemented like this, but maybe you you allow a process to run for a certain chunk of time, and the more CPU time that it gets, the less important it becomes. And and then the scheduler decides who is the most important process to run right now. And so you just, in order to balance things out, you age processes, and as they get quote unquote older, their priority decreases. Okay? So this approach is not appropriate for real-time systems. Why would it not be appropriate for real-time systems? Other than this explanation that I've put up there. Garrett.
Yeah, sometimes, like, you have to guarantee some amount of time for some process. You don't know how long it's going to take for something to age and get switched out.
So the problem is we have to interact directly with our environment, and the time at which we interact with our environment is dictated by the environment. It's dictated by physics, not based on fairness and convenience of which process gets allocated to the CPU. We have to interact based on what physics dictates. Otherwise, your analog brake system won't work right. Okay? So time is dictated based on the environment in which the computer is placed. So aging monkeys around with the time that a process can respond to its environment. So we don't like monkeying around with that. So aging is not necessarily appropriate for real-time systems. Soft real-time systems in certain contexts, yeah, maybe. But for hard real-time systems, not appropriate. Okay. The student scheduling algorithm, or earliest deadline first. Okay. this is another formulation of dynamic priority assignment that is often used in embedded systems, not universally, but often. EDF. So instead of having the fixed priority assignment that we dealt with before, we formulate EDF like this. All processes have a period. All processes have a deadline. Okay? So we have to make sure that we know what the deadline of the process is, again, on a fixed global timeline. Okay? With our initial process model, we had all, for all of our tasks, for all I in the set of tasks, T sub I equal D sub I. So what this meant is that the deadline of a task is equal to its period. Okay? So it's not necessarily always the case that the deadline of a task is equal to its period, but it makes no sense for the deadline of a task to be after its period. So you could have it be sooner. But for the sake of argument, for the sake of giving an earliest deadline first context, we can continue with this assumption that the deadline of the task is equal to its period. So EDF, your scheduler, instead of querying a priority queue to say who's the highest priority task, what you do is you say which task has its deadline coming soonest. So if I have 10 tasks all competing for the CPU, and one of them has its deadline in 2 ticks, another one has it in 10 ticks, another one has it in 5 ticks, another one has it in the next tick, I'm going to pick whoever's deadline is coming soonest to allocate to the CPU. Okay? So every time you invoke the scheduler, you look for the task with the soonest deadline, and you schedule that task. And again, this isn't, these deadlines have to be measured on a global timeline. Unlike your compute time, where your compute time says, eat 10 cycles, I don't care when, this is kind of like your period. You say, my period is up at clock cycle number 2470. So you see, what is the cycle time now? What is the time at which I need to be done? So at the time that I need to be done, take the difference between now and the time I need to be done, find the one whose time that needs to be done is soonest to now, and that's who you give the CPU to. So you have no notion of fixed priority. So there isn't a notion of who is highest priority. And not only that, you can't use a priority queue because of the fact that whoever gets the CPU time, their time is changing. As the scheduler runs, you kind of need to resort your priority queue, quote unquote. So a priority queue data structure for implementing EDF is not necessarily appropriate. Okay, so you run through all of your tasks, figure out whose deadline is soonest, and then you schedule that one. Why would you want to use EDF? EDF is, so with our fixed priority assignment, we had a nice straightforward, simple manner of allocating priorities, a nice straightforward, simple manner of picking who should run. That's the highest priority. It works great. Why would we want to do EDF? Liu and Leyland implemented the following. They said with independent tasks, if you can prove this, that the sum of the net utilizations of all the tasks in the system is less than or equal to 1, then you have a guarantee of schedulability. With rate monotonic analysis, if you remember, fixed priority scheduling, that bound was this n times the quantity 2 to the 1 on n minus 1. So, you know, as you with a large number of tasks, this inequality here, this value, this bound represents about 69%. With EDF, you have a guarantee at 100%. With fixed priority scheduling, you have a guarantee at 69%. So this is the pessimism of fixed priority scheduling. You can overcome the pessimism by using EDF. So, and again, that's not to say that you can't schedule sets of processes with fixed priority scheduling where the utilization bound is violated. You should have observed that by now. But you just don't have a proof of schedulability using utilization bound analysis. So why don't we use EDF? Well, it's harder to implement and it's harder to analyze. Harder to implement in the sense that you've got to scan through all of your tasks and find whose deadline is soonest in order to do the scheduler. Harder to analyze. It's not, you can't just say at the critical instant what's going to happen because of the fact that it's not so predictable because you're doing dynamic priority assignment. It's not clear when the program starts running who's going to run next, who's going to run next, who's going to run next. Okay? How do you handle a task without a deadline? Like the user interface task. When does the user interface task get to run? Okay, and the other thing, and this is probably the biggest shot against EDF, is when you have an overload situation. When you needed to drop a packet, or when you've got when you're needing to overutilize your CPU, but you have to run anyway. The fixed priority scheduling behavior is more predictable. So you know what's going to happen when you've got too many tasks that want the CPU with fixed priority scheduling. You know that the lower priority tasks are going to be starved. With EDF, you're going to be all across the board trying to make everybody work, and somebody's going to miss deadlines, and it's harder to predict exactly what's going to happen. Okay. And also, just given the fact that if we're choosing to use EDF because of the less pessimistic proof, we already know that you can still schedule even when the utilization bound analysis tells you you can't, or tells you that you have no proof of schedulability. On top of that, you can use the response time analysis to do a less pessimistic proof. Okay, so what happens if you're using fixed priority scheduling, but you have a situation to where your deadline is less than your period? So we've been operating completely under the assumption that our deadline is equal to our period. Well, what happens if we've got a system to where we want to say we've got a set of deadlines, and those deadlines are on a per task basis, and that is, when you release a task, it's got a certain amount of compute time that it's got to do, and then it's got a deadline that it's got to complete it by, and then it'll have a period that it gets reinvoked at some later time. So this is what we call, this is where you have the deadline of a task less than its period. So what if we do that? Do we want to change fixed priority assignment? So what we do is we assign priority based on deadline. So instead of based on period, so if you're doing deadline, if you've got a deadline that's not equal to the period, you assign the priority actually based on the deadline. So if the deadline of task I is less than the deadline of task J, the priority of I gets to be higher than that of J. Okay? So the book also has a proof on this. They call this deadline monotonic priority ordering, or DMPO, deadline priority scheduling, DPS. But basically, what we claim here is that if you assign priorities based on this, where you say if higher priority goes to whoever has the soonest deadline, in a static sense, not in a dynamic sense, but if you just say the soonest priority or the soonest deadline gets the highest priority, the same rate monotonic stuff applies. All right. Any questions about that stuff? Okay. I have had an exam question on the final before where I've said just implement EDF. Sometimes it works out well. Sometimes it's a complete disaster. Just be ready.
Yeah.